Today we're going to calculate the pH of a buffer solution. Buffer solutions are very handy. We use them all the time. One example of a buffer solution is the buffering solution of blood, which maintains our pH around 7.4. These are solutions that contain a weak acid or weak base and its conjugate acid or base. It applies the common ion effect in order to maintain a stable pH. The example I'm going to look at is a buffer solution made of benzoic acid and sodium benzoate. You may have seen sodium benzoate. Just look on the back of many prepared foods. It's a common preservative. And benzoic acid has a pKa of 4.19. We're going to look at solving these pH buffer solution problems with two methods. One, we're going to use the ice table method, initial change equilibrium. And the second method, we're going to use the Henderson-Hasselbalch equation. I'm just going to abbreviate HH equation. And it's important to note that these really are the exact same method. It's just the Henderson-Hasselbalch equation is in a more convenient form that allows you to solve these problems a little bit quicker. But the basis is really going to be in these reactions. So let's look at our reactions that we have going on in our buffer solution. So we have our sodium benzoate, which has a formula, NaC7H5O2. This is a salt, and it will completely separate in solution, or completely ionize, so Na plus the benzoate ion. So initially I had 0.15 molar of our sodium benzoate, so I actually have 0.15 molar of my ion and 0.15. So 0.15 molar of my sodium cation. My sodium cation here is going to be in the solution. It'll just be neutral. It's going to be a spectator ion. So it's going to be there, but it's really not going to contribute to the pH of my buffer solution. It's a neutral cation because it's a cation of a strong base. But our benzoate ion is going to be important. It's going to act as a weak base in our solution. So I'm just going to write that in. It's going to be a weak. So I'm going to highlight that. Also present in this solution is the benzoic acid, which is going to be our acid in solution. So you'll see that we're going to create a solution with both an acid and a base. So we have our benzoic acid. Let's label that. As our weak acid. And we know the equilibrium relationship for our acid here. We're going to write our Ka expression. So plus H2O. If it's a weak acid, that's going to donate the proton to water. We're going to write our reversible arrows. H3O plus. And then I gave a Ka for this expression, or a pKa in this case. So pKa equals 4.19. And pKa is the same kind of idea of pH. It's the negative log of the Ka. If I want to get the Ka, I'll show you how to do that in a minute. The Ka is just going to be 10 to the negative pKa. So I'll drop that up here. Ka equals 10 to the negative pKa. So we can set up an ice table here. Notice one thing we have going on. We have a common ion. So we have our weak base that we're adding, and then we also have that same weak base that shows up in our equilibrium expression as the conjugate base of our acetic acid. And this is what's going to allow our buffer to behave and maintain its pH. So let's look at our ice table. So our initial acetic acid in the problem was 0.10 molar. We have no water, or the water is there, it's just not important in terms of this calculation. And then our buffer, our weak base was 0.15. And so this is going to be a little different than some of the previous ice problems that we've done. We're going to have products at the beginning, though we did see some problems like that back in chapter 13. And then our H3O plus at the beginning is negligible, or 0. Our change so we're going to go to the left. We're going to the product side. I'm going to change to minus x, the water, don't worry about that, and then our plus x. And we're always going to go to the products because we don't have any of our H3O plus to begin with. So our equilibrium expression, 0.10 molar minus x, 0.15 plus x, and then plus x. The expression that we have written is Ka, because we have acid plus water, so this is Ka. And it's still are going to be our products over our reactants, so 0.15 plus x times x all over 0.10 minus x. And our Ka is equal to 10 to the minus pKa, which should give you 6.45 times 10 to the minus 5. When solving this, as with most problems in the pH chapter, we're going to assume small x. To simplify our life. And you solve for x out of this algebra, and you get x is equal to 4.37, 4.3 times 10 to the minus 5th molar, and that equals our H3O plus, which leads to a pH equal to 4.37 if I take the negative log of that number. Notice here the pH and the pKa are not all that different. That is a function of a good buffer. And we'll get into that when we start seeing what happens when we add an acid or a base to this buffer. Now the next method, so this is the ice table method. The next method is going to be using what we call the Henderson-Hasselbalch equation. And this equation is from the Ka expression. So if we have the Ka expression, just if I go in and I manipulate this mathematically by taking the negative log of both sides, you can relate this back to negative log of Ka is just pKa. And then you get the negative log of the pH minus log of A minus over HA. And we relate this back to the pH, just solving for pH equals pKa plus the log the A minus over the HA. And when we're doing this again, we're going to assume small x. And so we can simply put in our initial concentrations of our materials. So we can solve for this particular pH. It's our pKa, which was 4.19, plus the log of our benzoate ion, which was 0.15 molar, all over the benzoic acid, 0.10 molar. And that also gives us 4.37. So that is a faster way than going through the whole ice table business, but you have to be very careful when you're using the Henderson-Hasselbalch equation because it's very easy to flip-flop this equation. Make sure, one way to simply memorize it is that it's always the same. When you're looking at the ratio, it should be in the same order. A minus over HA is going to be the relationship. And you can also look at this, if you have more conjugate base than you have of the conjugate acid, you should have a pH, of the acid, you should have a pH slightly greater, slightly more basic than your pKa. If you have more of your acid than you do of your conjugate base, you should have a pH slightly less. So make sure your pH number at the end result makes sense. Henderson-Hasselbalch equation is great. It allows for very quick calculations of buffer pHs. It's just you have to be extraordinarily careful in keeping it from getting flip-flopped. I recommend going through and practicing this derivation because in a pinch you can always go back and derive it if you get messed up and can't quite remember it. And I know that that's something I have to do quite often because I tend to get things flip-flopped around, and that's why I rely a lot on my reactions. And then you can always do the ice table method as well. So that is calculating pH of a buffer. Now in the next few videos we're going to follow up with how to see what happens to this particular buffer if I add an acid or a base to it, and then we can really see the power of how this buffer is going to work. Until next time.